This is an object, if that is the size of it, that is 1,000,000 times more massive than the previous interstellar objects we've seen, and that's quite unlikely. There is not enough material in interstellar space to bring such a huge
the fact
object.
that it's unusually large is what's making you doubt that or at least be open to the possibility that it's not just a comet?
That's one aspect, and the second is that the trajectory is aligned with the plane of the planets around the sun. Now, we will get a good...
What if I told you an object from outside our solar system is emitting nickel, but no iron, a chemical signature that until now only existed in industrial processes here on Earth? This isn't science fiction, it's 3I Atlas, and it might be the strangest interstellar visitor we've ever seen. The most startling and arguably revolutionary revelation about 3I Atlas comes from observations made by the Keck II telescope at a formidable distance of 2.75 astronomical units from the Sun and 2.6 AU from Earth. The Keck Cosmic Web Imager meticulously captured the gas plume spectrum emanating from 3I Atlas. What it unveiled was a spectral fingerprint that sent shockwaves through the astrophysical community. Prominent nickel emission, starkly contrasted by a complete, inexplicable absence of iron. Let that sink in for a moment. This isn't just unusual, it's a chemical signature that on Earth has been almost exclusively associated with industrial processes, specifically those involving the synthesis of nickel alloys through the carbonyl chemical pathway. To find such a specific, technically demanding chemical output occurring naturally on a celestial body light years from any known industrial activity is nothing short of groundbreaking. It forces an immediate existential question. How? How could an object naturally formed in an entirely different star system exhibit a chemical output that on Earth is the hallmark of advanced technological or highly specialized geochemical processes? The proposed explanation, however mind-bending, suggests that this carbonyl process might occur naturally near the nucleus of 3I Atlas, leading to this peculiar and intense nickel concentration. But what kind of astrophysical environment could foster such a specific and rare chemical reaction on a cosmic scale? Typical comets and asteroids, the icy and rocky remnants of planetary formation, are expected to contain a mix of elements, often with iron being far more abundant than nickel. Iron and nickel are generally found together in cosmic bodies, a legacy of their formation within the stellar furnaces and subsequent condensation in protoplanetary disks. The highly selective emission of nickel without its common cosmic companion, iron, fundamentally challenges our understanding of the elemental compositions of objects forming in other stellar systems. This anomaly could hint at a truly exotic origin. Perhaps the 3I Atlas is a fragment of a highly differentiated exoplanet, one that underwent geological processes so extreme that heavy elements were stratified in ways we can barely conceive. Or perhaps it formed in a unique stellar environment, a peculiar type of protoplanetary disk where nickel was disproportionately abundant or chemically sequestered from iron in a way that allowed for its specific inclusion in 3I Atlas. It might even point to entirely undiscovered natural chemical pathways, hitherto unobserved in the vast laboratory of space, pathways that defy our terrestrial-centric understanding of geochemistry. The answer, whichever it turns out to be, holds the potential to revolutionize our comprehension of planetary composition and formation beyond our own sun. Further detailed analysis of these astonishing Keck images provided even more granular insights. The observations showed that the nickel was centrally concentrated relative to cyanide within the surrounding gas plume. This spatial differentiation is critical. It suggests that nickel is being released from a specific, perhaps warmer or chemically more active region of the nucleus, implying a localized source or a particular release mechanism that differs from the broader distribution of other volatiles. Cyanide, a more common cometary volatile, was dispersed over a larger area, indicating a more general outgassing. This distinction hints at a complex internal structure and varied volatile release dynamics within 3I Atlas. The emission profiles for both nickel and cyanide were also strikingly asymmetric, extending in both solar and antisolar directions, indicating a clear antitail. This antitail, an extension of material towards the Sun, had also been observed in earlier Hubble Space Telescope images from July 21, 2025. Such a feature is unusual for dust, which would typically be pushed away from the Sun by solar radiation pressure, forming a traditional cometary tail. The presence of an antitail for both gas species points to complex ejection dynamics, possibly linked to the object's rotation, localized vents, or specific volatile properties. Quantifying these releases, the trace mass loss rates were measured at 3.9 grams per second for cyanide and a significant 0.9 grams per second for nickel. While these figures might seem small in isolation, they are set against a staggering total mass loss rate of 150 kilograms per second, which is predominantly composed of common cometary volatiles: CO2, 87%, CO, 9%, and water, 4%. The stark contrast between the dominant bulk composition and the anomalous trace elements underscores the uniqueness of the nickel finding. Critically, the production rate of nickel relative to cyanide in 3I Atlas is significantly higher than what was observed in 2I Borisov and vastly exceeds the median for comets in our own solar system. This quantitative difference further solidifies its status as a geological and chemical outlier, an object that refuses to conform to the established norms of cometary science. This nickel without iron phenomenon is not merely an interesting detail, it is a monumental mystery. It forces us to ask whether the 3I Atlas is a fragment of a highly differentiated exoplanet where industrial-scale processes truly exist, or if it points to an entirely new, undiscovered natural chemical pathway unique to certain types of stellar systems. The answer could force a seismic shift in our understanding of planetary composition and the very building blocks of life itself, far beyond the familiar bounds of our cosmic home. As if the nickel anomaly wasn't enough to secure its place in the annals of cosmic oddities, 3I Atlas has also demonstrated an astonishingly high rate of water loss, earning it the evocative moniker of a cosmic hydrant. Using NASA's Neil Gehrels Swift Observatory in July and August 2025, scientists were able to detect the unmistakable ultraviolet glow of hydroxyl, or OH. Hydroxyl is a crucial biomarker for water in space, as water molecules, H2O, are readily broken down into hydrogen and hydroxyl radicals by solar radiation. This detection unequivocally confirmed that 3I Atlas is actively losing water at an estimated rate of approximately 40 kilograms per second. What makes this level of activity so profoundly remarkable and anomalous is the distance at which it is occurring. When these observations were made, the 3I Atlas was situated approximately 2.9 times farther from the Sun than Earth. At such a considerable distance, the solar radiation reaching the comet is significantly weaker, and water ice on a typical solar system comet would usually be too cold to sublimate so readily and vigorously. Yet 3I Atlas is behaving with the activity levels one might expect from a far closer-in comet, defying the conventional understanding of cometary thermal physics and volatile release. This unexpected hyperactivity has prompted scientists to explore novel explanations. Researchers estimate that at least 8% of the comet's surface is actively contributing to this prodigious water output. This fraction is surprisingly high when compared to typical solar system comets, which usually exhibit activity over only a small percentage of their surface at similar distances. The implication is that a substantial portion of 3I Atlas is engaged in releasing volatiles, or that the mechanism of release is exceptionally efficient. One intriguing hypothesis put forth to explain this phenomenon suggests that the comet might be surrounded by a cloud of icy debris. This debris, perhaps shed from the main nucleus or existing as a component of the comet's inherent structure, when exposed to sunlight would act as miniature steam vents. These numerous small icy fragments could efficiently sublimate and release water vapor even if the primary surface ice of the main comet nucleus remains too cold to undergo direct, large-scale sublimation. Such a scenario could imply a particularly porous, fractured, or recently fragmented nucleus, presenting a larger effective surface area for volatile release than its solid dimensions might suggest. It challenges the classic image of a comet as a simple, dirty snowball with a relatively uniform surface. This level of activity, coupled with the extreme distance from the Sun, is another significant deviation from standard cometary behavior, further perplexing models of how comets evolve and how their volatile materials are released. The sheer volume of water being ejected, alongside its unique nickel-rich composition, paints a picture of an object unlike anything we have encountered before. It forces us to question whether the mechanisms of volatile release for interstellar objects are fundamentally different from those of their solar system counterparts, perhaps due to their formation conditions in distant alien stellar nurseries. While its chemical composition and volatile release mechanisms are profoundly mysterious, 3I Atlas's physical characteristics also add layers to its enigmatic profile. Dr. Avi Loeb, a prominent astrophysicist at Harvard, has eloquently delved into the very gravity of 3I Atlas, concluding that its significance lies less in its actual gravitational mass and more in its attention-grabbing gravitas, its profound capacity to draw scientific attention and inspire new thought. Estimates place 3I Atlas's diameter in a considerable range, between 5 and 46 kilometers. This wide range highlights the current observational challenges in precisely determining its size, yet even at the lower end, it's a substantial object. For an object of this considerable size, its rotation period has been measured at 16.16 hours. Crucially, calculations show that this rotation rate results in a surface rotation speed that is considerably slower than its gravitational escape speed, which is estimated to be between 1.3 and 12 meters per second. This is a key insight. It implies that 3I Atlas is held together by its own gravity, not merely by the cohesive strength of its material. This characteristic distinguishes it from smaller, more loosely bound rubble pile asteroids or cometary fragments, suggesting a more robust, gravity-bound structure. With an estimated mass exceeding 33 billion tons, 3I Atlas is undoubtedly a massive celestial body. However, despite this impressive bulk, its gravitational influence is surprisingly weak on cosmic scales. As Loeb points out, its gravitational kick on nearby planets like Mars during its flyby would be unmeasurable. This reinforces the idea that its gravity, in terms of scientific intrigue, far outweighs its physical pull, reminding us that an object's cosmic importance isn't always tied to its ability to tug at other worlds. Another curious detail adding to its distinctiveness is the absence of a typical cometary dust tail in white light images. A standard comet approaching the Sun would typically develop a prominent dust tail, formed by fine particles ejected from the nucleus and pushed away by solar radiation pressure, scattering sunlight and making the tail visible. The fact that 3I Atlas lacks such a feature, despite its significant outgassing of volatiles like water and CO2, aligns with its unique chemical releases and suggests a complex interplay of forces and materials at play, rather than the straightforward dust and gas expulsion characteristic of familiar comets. Perhaps its material is too coarse, or its dust-to-gas ratio is unusually low, or the dust itself has properties that make it less susceptible to solar radiation pressure. Whatever the reason, it further complicates its classification and deepens the mystery surrounding its formation and evolution. The 3I Atlas is not just a scientific curiosity confined to telescopic images. It is a celestial traveler on a well-defined, albeit temporary, path through our solar system. Currently, it resides in the constellation Virgo and is approximately 362.5 million kilometers, or 2.42 AU from Earth. With an estimated apparent magnitude of 14.94, it remains a challenging but accessible target for powerful professional telescopes and dedicated amateur astronomers.
Well, it's something we've never seen before in solar system comets. But these are icy rocks that are in our backyard. And in fact, the question is whether similar rocks are made near other stars. And we might be up for surprises. In particular, there is a trajectory which is perfectly aligned with the plane of the planets. And that is something that cannot be explained just by observing or imaging it. It's really...
Its journey through our stellar neighborhood includes several significant milestones. The closest approach of 3BI Atlas to Earth within this century is anticipated for December 19, 2025, when it will pass at a substantial but observationally significant distance of about 268.9 million kilometers, 1.797 AU. Prior to this Earth flyby, the comet is predicted to pass its perihelion, its closest point to the Sun, on October 29, 2025, at a distance of 1.356 AU from the Sun. These close approaches to the inner solar system, particularly the perihelion passage, are crucial for scientists as they represent periods of heightened activity and optimal viewing conditions. The definitive proof of 3I Atlas's interstellar origin lies in its orbital parameters. Its orbit exhibits an astonishing eccentricity of 6.139 and an inclination of 175.11 degrees. An eccentricity greater than 1 signifies an unbound hyperbolic trajectory, meaning the object is not gravitationally bound to our Sun and will escape our solar system to return to interstellar space. The high inclination, close to 180 degrees, indicates a retrograde orbit, moving in the opposite direction to most solar system bodies. These parameters unequivocally confirm its status as an alien visitor, a fleeting guest offering a limited window for observation before it slingshots back into the vast emptiness of the interstellar void, carrying its secrets with it. Fortunately, the scientific community is well prepared to exploit this transient visit. Astronomers are poised to gather more crucial data, with a series of high-profile observations planned that promise to shed further light on this perplexing object. These missions are not just about seeing 3BI Atlas, they're about understanding its fundamental nature, its origin, and its implications for astrophysics. The HiRISE camera on the Mars Reconnaissance Orbiter, MRO, is expected to capture images around October 2, 2025. HiRISE, known for its exceptionally high-resolution imaging capabilities of the Martian surface, could potentially provide unprecedented detail. Its vantage point from Mars will offer a different perspective than Earth-based telescopes, potentially resolving features on the nucleus or providing fine detail on the morphology of its gas and dust plumes, which could be critical for understanding the source regions of its anomalous emissions. Following this, the European Space Agency's Jupiter Icy Moons Explorer JUICE spacecraft will have a unique opportunity to observe Atlas in November 2025, after its perihelion passage. JUICE, designed to study Jupiter and its icy moons, carries a suite of advanced instruments. Its observations will be particularly valuable as they will occur after the comet has experienced its maximum solar heating, potentially revealing changes in its activity or shedding light on how its volatiles react to increased energy input. JUICE's instruments, including optical cameras, spectrometers, and magnetometers, could provide invaluable data on the comet's overall morphology, the composition of its coma, and potentially even interactions with the solar wind, offering a more complete picture of its dynamic behavior. Finally, the Juno spacecraft, currently in orbit around Jupiter, is slated to make observations of Atlas in March 2026. Juno is equipped with powerful cameras and scientific instruments designed to study Jupiter's atmosphere, magnetosphere, and gravity field. While its primary mission is Jupiter, its instruments could provide complementary data to JUICE, especially on the faint outer coma or distant dust trails. The synergy between these three distinct observation platforms, Earth orbiting Hubble, past data, Mars orbiting HiRISE, Jupiter-bound JUICE, and Jupiter orbiting Juno, promises to create an unprecedented dataset, offering multiple perspectives and instrumental capabilities to peel back the layers of mystery surrounding Atlas. These upcoming encounters are not just observational events, they are vital scientific expeditions, poised to provide high-quality, close-range data that could be instrumental in unraveling the fundamental mysteries of Atlas. A universe of unseen wonders, the broader implications and speculative horizons. The story of Atlas is far from complete, but its current chapter has already rewritten pages in the textbooks of astronomy and astrochemistry. The sheer peculiarity of its chemical composition, the prominent nickel without iron, indicative of processes hitherto confined to terrestrial industry, alongside its anomalous water emission at unexpected distances, forces us to confront the profound possibility that the universe is far more diverse and chemically complex than our current models predict. This object is not just an outlier, it is a profound challenge to our cosmic self-perception. Implications for astrobiology and exoplanetary chemistry. The nickel without iron signature, if confirmed to be a result of a natural carbonyl process, opens up new avenues for astrobiological thought. If such complex chemical pathways can occur naturally on an interstellar object, what does this imply for the chemistry of exoplanets? Could there be planets where these nickel carbonyls play a role in unique forms of geology or even biology? Furthermore, if Atlas is indeed a fragment of a highly differentiated exoplanet, it offers us a tantalizing direct glimpse into the internal processes and elemental partitioning of worlds orbiting other stars. The water it is spewing, in such copious amounts, also underscores the potential for interstellar objects to ferry crucial volatiles, including the building blocks of life, between star systems. Could objects like Atlas be silent carriers, seeding the galaxy with the ingredients necessary for life, or perhaps even with prebiotic molecules far more complex than simple water? Rethinking exoplanetary system formation. 3I Atlas also provides a direct, albeit enigmatic, sample from another star system, allowing astronomers to test and refine theories of planetary formation. What does its nickel-rich, iron-poor composition tell us about the protoplanetary disk from which it originated? Was it a disk around a star with an unusual metallicity, or one where extreme chemical fractionation occurred? The fact that it is so different from our own solar system comets suggests a remarkable diversity in the materials and processes that coalesce to form planets and smaller bodies around other stars. It forces us to broaden our expectations for the average composition of alien matter. Are nickel-rich worlds more common than we imagined? The challenge to cometary classification. Perhaps one of the most immediate impacts of 3I Atlas is its profound challenge to our very categorization of celestial bodies. Is it truly a comet? Its rule-breaking nature, the nickel, the water activity, the lack of a dust tail, makes its classification as a familiar comet increasingly difficult. It defies the established norms to such an extent that it might necessitate the creation of a new classification. Is it an interstellar wanderer, an exocomet, a geochemically unique transient, or something else entirely? Its existence pushes the boundaries of our taxonomic systems, forcing us to recognize the vast, unexpected diversity of objects that can traverse the interstellar medium. The Oumuamua and Borisov precedent. 3I Atlas is the third interstellar visitor, but it stands out even among its unique predecessors. Oumuamua, the first, captured imaginations with its highly elongated shape and unexplained non-gravitational acceleration, leading to speculative discussions about artificial origin. 2I Borisov, the second, was more recognizably cometary in its behavior, but still an exciting direct sample from another star. 3I Atlas, however, distinguishes itself with its chemical peculiarity. While Oumuamua presented a mystery of shape and motion, and Borisov confirmed the presence of normal comets from other systems, 3I Atlas offers a profound mystery of composition. It suggests that interstellar space is not just teeming with diverse objects in terms of their physical characteristics, but also in their fundamental chemical makeup, hinting at an even greater range of stellar nurseries and planetary formation pathways than previously conceived. The human fascination and the search for technosignatures, careful speculation. The industrial process chemical signature of 3I Atlas, while currently attributed to a natural process, inevitably sparks more speculative, albeit scientifically cautious, discussions. If such a signature were truly impossible to explain naturally, it would push the boundaries towards considering artificial origins, similar to some of the initial, and later largely refuted, discussions surrounding Oumuamua. While the scientific community remains firmly grounded in seeking natural explanations, the very fact that 3I Atlas's chemical profile mimics an industrial process here on Earth adds a layer of cosmic wonder and encourages us to constantly reevaluate the limits of what is natural in the universe. It reminds us of humanity's deep-seated fascination with the unknown, the allure of a messenger from another star, and the profound questions it poses about life beyond Earth. As 3I Atlas continues its fleeting journey through our solar system, it carries with it not just its peculiar chemical payload and surprising activity, but also the potential for paradigm-shifting discoveries. Each new piece of data gathered from telescopes and spacecraft is like a fragment of an alien puzzle, offering tantalizing clues to the nature of worlds beyond our Sun. The answers that unfold in the coming months from the HiRISE, JUICE, and Juno missions may well redefine our understanding of cosmic chemistry, the incredible diversity of objects traversing the interstellar void, and perhaps even the very definition of a comet. The 3I Atlas isn't just an object, it's a profound mystery, a whisper from another star system, urging us to question everything and embrace the infinite possibilities of the universe. It stands as a powerful testament to the fact that just when we think we understand the cosmos, an interstellar visitor arrives, breaking all the rules and reminding us of how much more there is to learn, to discover, and to marvel at in the vast, strange, and endlessly captivating expanse beyond our home. Its legacy will not merely be its unique composition or activity, but its enduring power to inspire wonder and push the frontiers of human knowledge.